Okay, this is lesson 1 review from grade 11 on function notation. So a function is a relation in which there is a unique output for each input. Each value of the independent variable, or the domain, or the x values, must correspond to one and only one value of the dependent variable, or the range, or the y value. So there's a few different ways we can express functions or represent them. We could look at a set of ordered pairs. We could have table of values. We could have a mapping diagram, and we could also have a graph. So let's start just by looking at these and determining if they are functions or not. So the first one here, this one, we can see that there's a unique output for each x value, for each input value. So this one is a function. The next one here, we can see that -2 and 4 is 0.0 and 0, 1 and 1, 2 and 4. So this one is a function as well. Because each x value has only one y value. What about this next one here? We've got 1 is mapping or has a point at 1, 2, and also at 1, 4. So that means that we would have a point at 1, 2 and a point at 1, 4. So if we think back to the vertical line test, this one would not pass the vertical line test because it would hit, if we had a vertical line at x equals 1, it would hit at values of y of 2 and 4. So this one's not a function. The next one, so we can see that -1 maps to -1 maps to -3, so that's a point, and then 1 maps to 0, so that would be another point, 3 maps to 2, and 5 maps to 2 as well. So that means that at the x value of 3 and 5, they both have a y value of 2. So that's okay, it is a repeating y value, but it would still pass the vertical line test. So this one is a function. Okay, so we can also look at these graphically. Okay, so if we think about the vertical line test, it can be used to check whether a graph represents a function. It shows that there's only one element in the range for each element in the domain. So basically, you run a vertical line across a function, and if it only touches in one spot, then you know that it is a function. So just draw a line across here anywhere. So if we draw a straight line there, only passes at one spot. If we draw a straight line anywhere across that function, we're going to see that it will pass the vertical line test. Okay, so let's look at the domain and range of this function. So to start off with, let's label the vertex down here. So it looks to me like that is -1, -3. You can see the zeros on here too. And so the domain and range are something else that we need to review from grade 11. So the domain states what happens with the x values. So the domain of x such that x is an element of the real numbers. So that's really all we can say about the x values, because you can see here that they're going to continue to grow towards positive infinity and towards negative infinity. Now the range we can give a bit more of a description about. So the range, y such that we can see that the y values are always going to be greater than or equal to -3. And then we also have to state that y is an element of the real numbers to show that all those points are included in between each integer. So let's look at the next example. Sometimes the domain and range of a function will need a restriction. So they'll need a restriction in order to properly define the particular situation. So this function, you can see here that there's a vertical asymptote here and a horizontal asymptote here. So this function would be just XER and YER, but because of these asymptotes, we know the function doesn't exist where the asymptotes are. So let's start by just writing down what those asymptotes are. So we're going to say that this one is, let's say there's an asymptote here, horizontal. And that's going to be at x equals 1. Okay, and then we're also going to note that there is a vertical asymptote. And that's going to be at, the horizontal asymptote was supposed to be y equals 1. And the vertical asymptote is, let's say it's at -2. So if we want to just see where those lines are, so we've got horizontal asymptote there, and then we've got the vertical asymptote here. Okay, so we've got our two asymptotes there. So those, and so now what we can say is we can say the domain is that x such that x cannot equal -2, where that asymptote was, and x is an element of the real numbers. And then we can say for y and the range, y cannot equal 1, and y is an element of the real numbers. Okay, so let's flip to the next example. Okay, so we can also find out if something's a function algebraically. So a function notation, f at x, is used to represent the values of the dependent variable in a function. So really, function notation is a good way of showing what you're subbing into the function to find out what the output value is. So you're showing what the input value is, or the x, and what the output value is, or the y. So function notation allows us to evaluate the function at different points. So here we've got two functions. We've got f at x and g at x. So let's start off by finding f at 2. So f at 2, and we're just going to sub 2 into the function. So 2 squared plus 3 times 2 minus 4, and that's going to give us 6. Next one's a little trickier. Same function. So f at 1/4 is equal to 1/4 squared plus 3 times 1/4 minus 4. And so we'll end up with some fractions. We need to find a lowest common denominator. So we'll just multiply the top and the bottom of 3/4 by 4 to get a lowest common denominator of 16. And then we'll multiply the top and the bottom of this one by 16. And we'll end up with -51/16. So the function's value at 1/4, an x value of 1/4, would be a y value of -51/16. Okay, so next one, same idea. We're just taking a plus 1, and we're going to sub it into the function f at x anytime that we see an x. So f at a plus 1, so I'll have a plus 1 squared plus 3x minus 4. Missed that one. Okay. Okay, minus 4. And then we'll end up with, once we FOIL this out and then put like terms together, we'll end up with a squared plus 5a, or we could write it in factored form as a times a plus 5. Okay, and the last one like this is f at g at x. So what we want to think about here is g at x is the input value. So we're going to take g at x, so we're going to take x plus 3, and we're going to sub it into f at x. So let's do that. Okay, so we're going to do f at, and then our g at x function is x plus 3. So we'll have x plus 3 squared plus 3 times x plus 3 minus 4. And then we'll expand this or use FOIL here. We'll distribute the 3, and we will end up with x squared plus 9x plus 14. Okay, so let's go on to our next example. Okay, given the following information about a function, sketch f at x. So we're given a bunch of hints about this function. So the first hints that we're given are that f at 7 is equal to f at 0 is equal to f at minus 2 is equal to 0. So what this is really telling us up here is that these are all the zeros. Okay, so at x equals 7, at x equals 0, at x equals negative 2, all those functions are equal to 0 in terms of y. So we can start by sketching those on. So f at 7, 0, negative 2. Okay, so we can start by sketching our zeros. And then it says for when x is between negative 2 and 0, and when x is bigger than 7, f at x is greater than 0 when x is between negative 2 and 0, and when x is bigger than 7. So those are a few more hints. So we're thinking about what's happening above the x-axis. So the points that are going to be above the x-axis are when x is between negative 2 and 0, and when x is bigger than 7. So when x is bigger than 7, will be above the x-axis, and also between negative 2 and 0. So we don't know exactly what this is going to look like yet, but it's going to be somewhere above. And then we're told that the function is smaller than 0 when x is smaller than negative 2, and when x is between 0 and 7. And then the last hint is that the domain is XER, and the range is y is bigger than negative 5. So we know that this function cannot go below negative 5, so there's an asymptote at y at negative 5. So this is going to come down, but not below negative 5, and this as well. We don't really know exactly what it's going to look like, but something like that is possible. Okay, because there is an asymptote at negative 5, right here. There's an asymptote there. Okay, let's go to the next example. Use a vertical line test to determine whether each relation is a function. Okay, so we'll use a vertical line test here. So we can see this one, definitely a function. Okay, and then we'll try the next one. So what about B? What do you think about B? So if we draw a straight line on B, we can see right away that it's going to fail the vertical line test because it touches in two spots there. So that is not a function. Okay, so far we've got a function. This one is a function. This one's not a function. And then if we look at C, we can see that the vertical line test would pass on C. And then let's also look at D. So D, it's not going to pass the vertical line test either. So let's just go back. So this one is a function, and this is not a function. Okay, and let's move on to the last slide here. Determine the domain and range of each function. Sketch a graph of each one. Okay, so this one is just a straight line, so y equals mx plus b. So we could say that the domain would just be, we can say x is just an element of the real numbers because it would continue to grow towards positive infinity and negative infinity and all the points in between. And we can also say that the range is just y is an element of the real numbers. And this function is just going to be a straight line that has a y-intercept of 5 and that has a rise over run of 2 over 1. So it's just going to look something like that. And the next one we know is a parabola. So we know the next one's a parabola. Let's just do a quick sketch of it first. We can see that the vertex is going to be at 1, 3. It's going to be up here. And we can also see that it opens up. So it's going to look something like this. So the domain for this one will be x is an element of the real numbers because the x values continue to grow towards positive infinity and negative infinity. Now the range, though, we can describe the range a little bit more. We can say that the y values are always going to be equal to or greater than 3. And y is an element of the real numbers. Okay. And we're going to go down to C. Okay, and for C, we can see that the function is going to have an asymptote at x equals negative 3. So because of this, which we'll be reviewing more, but there's going to be an asymptote at negative 3. And we can see, if we recall from starting to graph these last year, this function actually looks something like this. This is very approximate. Ooh, that was a bit rough, but okay, so now we've got the function. So we can see for this one, yes, it is a function. And so if it is a function, we can state what the domain and range are. So the domain for this one will be x such that x cannot equal negative 3, and x is an element of the real numbers. And the range, we can say that y cannot equal 0, because there's another asymptote along the x-axis, and y is an element of the real numbers. And that's it for this lesson.